I want to talk about a couple of things having to do with type 2 problems. These are the problems when you throw something at an angle and it lands at the same height. Sort of like one kid over here tossing a baseball to his friend over here. And so this position versus time graph looks exactly like the position versus time graphs that we've had before. But just remember, this is for an object that's moving through time. And so this, while this is the time, this could also be the x position. And maybe I'll keep it at that so that things are a little bit more clear. So I want to think, well, okay, if I start off with some initial velocity here, what happens to the velocity and the acceleration as you travel to these different points? And these points that I'm putting on here are sort of special in that these two will be at the same height, these two at the same height, these at the same height, and this one at the top of its motion. So the first thing, just what does the acceleration of this object look like as it's traveling this path? Well, the acceleration, no matter where you're at, no matter where the ball is, gravity always pulls it straight down. And so this ball's acceleration will always be straight down, and it will be the same throughout the whole path. Even at the top, this ball is accelerating downward the whole time. The whole time. Okay, and so the velocity then, well, what does that look like? Okay, so this is shot at some initial velocity here at some angle theta. And so over time, this ball travels and its direction of the velocity changes. You can see that as the slope of this line changes. If this was a position versus time graph or a height versus time, the slope changes, the velocity changes. As a position versus position graph, height versus distance, this velocity becomes more and more horizontal over time. I'm gonna change these vectors real quick. Okay, so the velocity will become more and more horizontal over time. It's gonna start off big, and of course, over time, the velocity will decrease. But at the top of its motion, this ball is still moving sideways. It's still moving from friend A to friend B. And so at the top of its motion, the velocity isn't zero. The vertical velocity is zero, but it still has some velocity. And then as this travels downward, you'd see that the total velocity here is the same as the total velocity here. The total velocity here is the same as it is here. And then here, it's also the same. And so what about the components of the velocity? Well, if we look at this x component of the velocity, if I've drawn these correctly, this green line, Vx, should stay the same for the whole time because this ball is not accelerating in the x direction. There's nothing pushing or pulling it in the x direction. In the horizontal direction, there's nothing pushing or pulling it once it leaves the person's hand. And so the velocity in the x direction is constant. The y direction is a little bit different. What color? We're getting so many colors on here. The y velocity is a little bit different. Let's just use this purple color. That y component of the velocity looks exactly like the y component of the velocity before, that it's upwards and getting smaller, and then at the top the velocity in the y direction is zero, and then it gets bigger as you travel downward. Now I can draw these y components of the velocity on this side, or I could have drawn them here to create the whole triangle of my components. So the velocity in the y direction will get bigger and bigger and bigger as it travels down, down, down. Now remember, this is just the same as a ball that's thrown straight up in the air, that the initial velocity, v naught, here is going to be the same as the final velocity here, total velocity. The components will be the same as well. All right, so remember the red is the acceleration, the orange is the total velocity, the green is the x component, and this purple gray is the y component. The next thing I want to talk about is what happens when you change the angle that an object is shot at. So if we keep the velocity the same, but we change the angle from something small and we increase that angle, what will happen to the range or the distance that that object travels? And I think it's better to look at this as a sort of vector component thing. And so if you don't give any if you don't give any vertical velocity, this object isn't going to go up in the air and come back down, right? With the same respect, if you take that angle and you make it 90 degrees, that object is just going to go straight up and straight down. And so you have this push-pull with giving it maximum vertical velocity so it spends the most time in the air, and maximum horizontal velocity so that your object can actually travel in that direction. And so as I change this angle, you'll see that this vector, or this velocity arrow A, which is 120 units in length, you can see that as it goes, the y value for the velocity is decreasing as the x value is increasing. And then if you increase theta, you get sort of the opposite. And so there has to be a point at which this distance that it travels, you've sacrificed that horizontal distance. Let's just decrease this. You've sacrificed this horizontal velocity for more vertical velocity, right? And so this object isn't going to go very far because you didn't give it enough horizontal velocity. And in the same respect, this object isn't going to go very far because you didn't give it enough vertical velocity. And so what you're going to see with that range, the distance that it travels, as you increase theta, is you're going to see that range is going to increase to a maximum value, and then the range is going to decrease again. And there's got to be some sort of math, blah, blah, blah in here. But you'll find that at an angle of 45 degrees, you've maximized both the x and the y initial velocities, and that will give you the maximum range. So I'm going to come back to here and just show you this picture. So this angle here, small angle, and this angle here, big angle, give you the same range, in this case 5. And so how is this angle, this little angle, related to this big angle? Well, if you take 90 degrees minus the little angle, that gives you like the second angle, and these two angles will give you the same range. As you increase the angle, that range will increase to an angle measure of 45 degrees, and then it'll decrease again.